Okay, in 8C, this problem might strike you as a little odd for a couple of reasons. First of all, they're asking you to calculate a standard electrode potential for a reaction that they've already provided that value for in an earlier problem. So if you were doing this right here, that you'll notice that they already provided that particular potential. All right, so notice that all these are part of question number 7, and this is part of question number 8. So that's why they're doing this the way that they are. You would not have had this previously presented. All right. Another thing about this is that there's an question 8b, which was not shown in your practice problem packet, and that showed that the delta G was this right here, and that allows you to use this equation right here to calculate an electron, a cell potential for that particular reaction. All right, and that would be needed in order to solve this problem the way that they would have expected it. All right, so putting that in for your for the potential for the entire cell, we could use the data booklet to figure out the cell potential for this oxidation half reaction, plugging that in, and we can calculate this value right here. And you can see that this is pretty close to the positive 1.44 that they did before, and the difference most likely occurs just because we're using a value that comes out of a calculation, which is going to involve some amount of rounding. And again, even in this calculation right here, we're going to round a value. So that's going to cause a little bit of a disparity. All right. Question 9, I'm going to go ahead and skip because there's this is fairly complicated. It involves putting some things in series, which is a fairly high-level concept, and I want to make sure that I'm not telling you something that is not untrue, or that make sure that I'm not telling you something that is untrue. So question 10, all right, they provide this information here, which in my opinion is redundant because all of this information right here is available in the data booklet. But when you're looking at this, just remember that the thing that's most positive most wants to happen as written, as that reduction. Things that are the most negative are things that would be most likely to occur in the opposite direction. All right, and if you're just looking at this, remember there's that rule of thumb. All right, the lower things on the list, the things on the left, they really want to get reduced. So that means that they would be the best oxidizer. Since they want to get reduced, their reaction accepts electrons, meaning that they could cause something else to get oxidized. All right, so the first question has to do with nickel and iodine, so we're going to look up those, compare those, and it says, what's the balanced equation? All right, well, what you need to do is figure out which of those is going to want to exist as the oxidation, which one's going to be the reduction. And if you look at the half cell potentials, this is the more negative of the potentials comparing these two, so that would occur in the opposite direction. So let's turn that around to an oxidation. And you could calculate that overall cell potential, but what it asks is for the overall reaction. So we're going to take these, and what you want to make sure is that you have the same number of electrons being transferred. So notice that we've got 2 electrons being transferred for both of these, so those are going to cancel out, and you just write what comes out when you do that. All right, and make sure that, again, when you're writing this down, to have the states of matter of these chemical species drawn in your final answer. All right. And the next one, it says basically give the direction of the movement of electrons if you hooked up the nickel half cell to the manganese half cell. All right. So again, we want to see, we need to determine whether things are going to exist as oxidation or reduction. Comparing these two, well, one thing that's a little bit odd about these is that they're both negative. All right. But remember, one of these is still more negative than the other. All right. So this is more negative, all right, meaning this one right here is more positive compared to this. So this would exist as the reduction, and we want to turn this guy into the oxidation, which means flip it around, all right? And so we would get this one right here, and we could show these. These would be the cell potentials. And the one thing that I want to point out about this is that if this is existing as the reduction, then this half reaction involves consuming electrons. Electrons are taken up as a reactant, and in the oxidation, electrons are produced. All right, so that's the way I view this. And so the way I would answer it is just to say it would flow from the manganese half cell to the nickel half cell, because the oxidation occurs in the manganese half cell, right, which is shown here, and reduction occurs in the nickel half cell. All right, and I think that would explain, assuming someone understands that oxidation means that electrons are going to be produced as part of that process, would make sense. All right, the answer that they give in the data booklet is just to state that Ni2+ is a stronger oxidizing agent than manganese. All right, so basically what that means is that nickel is going to be, since it's, what it means to be a stronger oxidizing agent is that it's more likely to be the thing that accepts electrons and gets reduced. All right, so in the next one, they ask you to actually calculate a cell potential comparing iodine and manganese. Again, we know that iodine, since it's the most positive, would exist as written. The manganese one you have to turn around. All right, and when you turn that reaction around as compared to how it's written right here, you would get this, and that would give you this as a final answer. And again, I should have put in a positive here. I have a question about whether they would take off for not having that. Generally, if you don't put a sign, it's assumed to be positive, but they seem to be sticklers for these potentials either having a sign shown. So definitely put in that positive here. All right. In 10, identify the best reducing agent. All right. So again, when you're looking at this, remember, the lower down on the list, the more positive things, those things, since they are things that want to get reduced, that means they themselves are oxidizing agents. All right, so these are your best oxidizing agents. The thing at the top would be your worst oxidizing agent, and your worst oxidizing agent, it's the thing on the other side, is going to be the best reducing agent. So the best reducing agent is this guy right here. And so that would be your answer. All right. So in 10, I want to go and start off by just pointing out a mistake that I made here. At both the cathode and the anode, I'm comparing a possible reaction to the reaction that could occur with water. All right. And so at the cathode, since that's where reduction occurs, I wanted to show the reduction of water. All right. And so if you do that, this should actually be H2, and this should be G in parentheses here for gas. All right, and I mistakenly wrote that as water. All right, so at the cathode, we've got concentrated sodium chloride. So the two possible reactions there would be the reduction of water or the reduction of your metal ion. All right, and since your metal ion is sodium, we know that sodium it's part of that group of metals. All right, so again, sodium is in this region right here where these are really high negative values, which means that the forward reaction does not want to occur. So sodium definitely does not want to get, sodium ion definitely does not want to get reduced. Therefore, that would make the reduction of water the preferred reaction. All right, at the other electrode, the anode, that's where the oxidation occurs. So the two possibilities are that the halide ions could get oxidized to make the elemental halogen, or you could get oxidation of your water molecules to make oxygen in this reaction right here. And in my opinion, they oversimplify this a little bit because according to the potentials, it seems like this would still possibly be the more preferred reaction. But what they really want you to realize is that if you get the concentration of the chloride up enough, you're going to get some amount. This becomes more and more likely. All right, and so what they're claiming is that chloride becomes the product at that anode. All right, my guess is that some combination of both of these probably is going to be occurring at that anode. But if you see concentrated something chloride, all right, what they're wanting you to realize is that the oxidation of the chloride is going to occur. All right, and just by comparison, if this had said dilute sodium chloride, this right here would be the preferred reaction, because what they want you to realize is that there's not enough concentration of that chloride ion around that electrode for that reaction to occur. All right, so these are the two answers that I would provide for those particular problems, and you can just read those yourself. All right, question 11. All right, so standard electrode potential, just the definition. It's the electrode potential in a half-cell reduction reaction under standard conditions when you're measuring it against the standard hydrogen electrode. All right, and remember to include the conditions. If it's a solution, it's got to be 1 molar. If it's a gas, it's got to be at 1 atmosphere of pressure. All right, and if you were to say here, instead of 1 atmosphere, say 100 kilopascals, that would also be acceptable. Okay, in 11b, it's a question about the oxidation numbers of the titanium in this. All right, so the initial oxidation number, well, this is the form of titanium right here. I could calculate that its oxidation number would be +4. Final oxidation number, well, it's titanium +3, so it's just going to be the charge, so it's +3. And so in going from +4 to +3, that involves the charge going down, so that would be a reduction. All right. One thing I do want to point out is that they are sticklers for how you write this. All right, and the criteria in the rubric for how they grade it, they make the statement: do not award for any of these right here. So if you wrote this as just plain old 4, all right, according to the rubric, you would not get credit for that. That seems a little strict in my opinion, but I would rather you provide it in the form that they want. All right, so in general, when you're doing oxidation numbers, all right, make sure that if it's positive, you show that plus sign. All right, so in 11c, consider the above equilibrium, predicting, giving a reason how adding more acid would affect the strength of this as an oxidizing agent. All right, so again, you can see that this is getting reduced, which means that this is the oxidizing agent. And we can see, okay, well, this is just a simple application of Le Chatelier's principle. If we increase the acidity, all right, if we make it more acidic, or how did they put it? They would say adding more acid. So if you add more acid, you're increasing the concentration of aqueous H+ ions. So that's adding to this part right here. That would tend to shift this towards the right, or another way of saying it, shift the equilibrium toward products. All right. So again, sometimes the language is used shifting it towards the right. The answer that they indicated moving the equilibrium toward products. So if you want to use language consistent with what they want, I would say products. All right, and because that happened, you can make the conclusion that that makes that a stronger oxidizing agent, because it favors that oxidation direction of that reversible reaction. Okay, so problem 11D is actually a pretty complicated problem, and so I'm going to go ahead and hold off, and because I just noticed something about it, and I want to. So don't disregard what I've got written down here. I'm going to redo that in the next video with my correct answer. All right, so in this problem, this is also fairly advanced. All right, and so essentially they're putting in some different ions into different half cells, and they're not giving you any indication about which way it would go. All right, so the way I recommend doing this is writing down these things as both a reduction and an oxidation, and then basically constructing this so that you could have some combination that would give you the most positive overall cell potential. All right, and the way that would work is if you had, at this electrode right here, you had your titanium 3+ getting oxidized, and in this half cell right here, you had your iron 3+ getting reduced. All right, and if that happens according to this equation right here, we would have this electromotive, this potential. This would be the potential of this over here, and if you add these together, that would give something like 0.83